This is part 1 of lesson 10.6, the ratio and root tests, and these are our last two convergence tests for our infinite series. So these two tests are great because they are very straightforward, there's no gray area, and they're for a series that are sometimes hard to look at because they can be quite complicated. But these make them seem like the easiest ones to find the convergence of. So let's start with the ratio test. So of course we have an infinite series, and it's a series of non-zero terms, and we have three conditions: either converges, diverges, or it's inconclusive. So if the series converges, and it converges, the nice thing is it doesn't just converge, it converges absolutely if the limit as n approaches infinity of a sub n plus 1 over a sub n, the absolute value of that, is less than 1. If that limit is greater than 1, then the series diverges. But if that limit equals 1, you can't use the ratio test, you have to use another test. So let's go through and do a couple of examples of this. Letter A, we have the summation from n equals 1 to infinity of 2 to the n over n factorial. And this is a great one to use the ratio test because it's a complicated series and it has two things that make it complicated and that are good for the ratio test. And those two things are an exponential and also a factorial. So to start this first one, I'm going to go ahead and write out my two terms here that I need to use, my a sub n. And you don't always have to do this. You can go right to your limit. And our a sub n plus 1 and then we are going to take the limit as n approaches infinity of the absolute value of a sub n plus 1, which is 2 to the n plus 1 over n plus 1 factorial, divided by 2 to the n over n factorial. You have to simplify that. If you want to show that you're multiplying by the reciprocal, you can do that if it helps organize this in your head. If you're fine with just simplifying the fraction, this step would be unnecessary for you. Oops. And that's fine. However, you want to show it, so this would be times, and then the bottom would be flipped over. So you would have the limit as n approaches infinity of the absolute value. So you're just left with 2, because the 2 to the n's would divide out, over just n plus 1, because all the other factorials will cancel out. And so we can see that this definitely equals 0, and 0 is less than 1. So we would say that the series converges and you could say absolutely the series converges absolutely by the ratio test. Okay, letter B. Again, we have a factorial and we also have an exponential. So let's go ahead and use the ratio test. So we're going to take the limit as n approaches infinity of, now this is going to give me n plus 2 factorial, because I'm adding n plus 1 over 3 to the n plus 1. And that's going to be divided by n plus 1 factorial, divided by 3 to the n. And then when this simplifies, we get n plus 2 on the numerator, and we get 3 in the denominator. And what we can see is that this is unbounded, so the series diverges. example 2, we're supposed to show that the ratio test is inconclusive for the following series. So one good thing is that these are all n's, but we want to show, so it'll make it easier to simplify a little bit. We want to show that the limit as n approaches infinity of a to the n plus 1 over a to the n equals 1. That's what we want to do. So let's go ahead and do that. So we have the limit as n approaches infinity of n plus 1 over the cube root of n plus 1. It's all divided by n over the cube root of n. Now when you go to simplify that, we can kind of, I think showing the reciprocal for this one makes it a little easier. So we're going to have n plus 1 in the numerator over the cube root of n plus 1 times the reciprocal, which would be cube root of n over n. Now what we can do is use some of our limit properties, and I can separate it this way. So let me put my n's together, since everything is being multiplied, and then put my cube roots together. So this is going to equal the first limit. This is going to equal 1. So I have 1 times, same with the second limit, 1, which is 1. So the ratio test, therefore, the ratio test is inconclusive. And just from the type of, and we're going to talk about this later in the lesson, just from the type of a sub n you have n over n to the 1/3. Why not simplify that and make that n to the 2/3? And we can see that that is a p-series and it diverges. So that would be much faster than doing the ratio test. And we're going to talk more, as I said, at the end of the lesson about the idea of how do you go about picking what convergence test. Sometimes you start down a road and you make it more complicated for yourself. So here is our last convergence test, the root test. So it works well for any series that involves the nth power. But this is an important note, it's not always conclusive for p-series. So because p-series usually n to a power, to a p power, so it's not the best test to use for p-series. They have its own test, so why not use that? So let a sub n be a series, and it converges again, absolutely, if the limit of the nth root of a sub n is less than 1, and it diverges if the limit of the nth root of a sub 1 is greater than 1, or it is unbounded, it equals infinity. And again, it's inconclusive if that limit is equal to 1. Now this test is great if you have something to the n power especially. It makes your life so easy. I'll show you. So in example 3, use the root test to determine whether the series converges or diverges. So we have e to the n over n to the n. So that is definitely to the nth power, so using the root test is great. So what we're going to do is we're going to take the limit as n approaches infinity of the nth root of the absolute value of e to the n over n to the n. And when we do that, what happens is we're just left with the limit as n approaches infinity. The powers are going to cancel each other out. We're just left with e to the n over, just e over n. because the nth power goes away. E over n. And that, of course, equals 0. And 0 is less than 1. So the series converges absolutely. By the root test. Okay, letter B. Now, the difference with letter B is that we have 3 to the n, but we have n to the third. So we have kind of a p series here, but we also have an exponential. But I like using the root test when I have anything to the n power because it simplifies it so much. So what I'm going to do is I'm going to take the limit as n approaches infinity of the nth root of n to the third over 3 to the n. And that's the absolute value of that. And so when I do that, I can simplify. And what I get is, in my denominator, I just have 3. And in my numerator, I'm going to have n to the 3 over n if I write it as a rational exponent. So now what's going to happen here is, as this gets larger and larger, let me rewrite this one more time here. Make it a little more simple. So I can pull that 1/3 out now. So maybe I'll make it a little easier to see. As this n gets larger, this whole exponent is going to go to 1 because you're going to have 3 over a super large number. So this is going to go towards 0. So you're going to have n to the 0. So you're going to have that your limit is 1/3 times 1, which is 1/3. And that, of course, is less than 1. So therefore, the series converges absolutely. By the root test. All right, in letter C, again, you can see that we have a series where the nth term is raised to the nth power. So we're just going to go ahead and apply our root test. So we're going to have the limit as n approaches infinity of the nth root of n to the over n plus 1 n to the third to the nth power. So that is going to equal the limit as n approaches infinity of the nth roots will cancel. So I am left with n over 1 plus n to the third. And this limit is going to equal 0, which is obviously less than 1. So again, the series converges absolutely. By the root test. Okay, so this is going to be the end of the first part of this lesson. And in the second part, we are going to talk about what are the best strategies for choosing the appropriate convergence test.